In this video, I want to give you all of the formulas that you need to know if you're learning probability in school. We're going to talk about the different types of symbols and notations you need to be familiar with, as well as the different types of probabilities that are out there, like marginal probability, union probability, joint probability, conditional probability, and even negation probability. We're going to talk about that. We're also going to talk about the difference between independent and dependent events and what it means when two events are mutually exclusive. So let's go ahead and begin. The first thing we're going to talk about is marginal probability. Even if you never heard of this term, you're familiar with this type of probability in most cases. Marginal probability is the probability of a single event occurring independent of other events. So let's say our sample space contains the numbers 1 all the way to 9. So all the whole numbers between 1 and 9. And let's say event A represents getting the outcomes 1, 2, 3, and 4. And let's say event B represents getting the outcomes 6, 7, and 8. And as for event C, we're going to say it corresponds to the numbers 1, 7, 8, and 9. So, given this sample space, what is the probability of event A occurring? So that would be an example of marginal probability. We want to calculate the probability of a single event occurring. The probability that an event will occur is equal to the number of successful outcomes divided by the total possible outcomes that exist. So in this problem, the probability that event A will occur, we have 4 successful outcomes out of 9 possible outcomes, so it's going to be 4 out of 9. Let's say if we want to calculate the marginal probability for event B. The probability that event B will occur is we have 3 possible outcomes, or 3 successful outcomes, divided by a total of 9 possible outcomes. So it's 3 over 9, which reduces to 1 over 3. Now 1 over 3 is basically 0.333 as a decimal. And so that corresponds to a 33.3% chance that event B will occur. If we want to calculate the probability that event C will occur, we have 4 out of the total 9 elements that are possible. So it's going to be 4 over 9. 4 over 9 is basically 0.4 repeated, so it's like 0.444. So there's a 44.4% chance that event C will occur. So that's an example of marginal probability. Now, there are some symbols that you want to be familiar with. This represents union, and when you see this, this represents intersection. For those of you who want more example problems on union and intersections, check out the links in the description section below. I'm going to be posting more videos there. So let's say if we want to find A in union with B, all we have to do is combine the elements that are in A and B. So A in union with B, that's going to be equal to the elements in A plus the elements in B. Now, let's say if we want to find the elements of when B is in union with C. So all we need to do is combine these elements, and we're not going to repeat any element twice. So it's 1, 6, 7, 8, and 9. If we want to find the intersection of B and C, they intersect at 7 and 8. So we're looking for the common values. Now, A and B, there's none. There is no intersection. So because A and B don't have common elements, A and B are mutually exclusive. And we'll talk more about that later. So now let's talk about something called union probability. Keyword union. What is union probability? This is the probability that either event A will occur, or event B will occur, or both event A and B will occur. That's union probability. In other words, it's equal to the probability that A or B will occur. This can also be represented as the probability of A union B, thus the expression union probability. Now we can calculate this using the numbers that we have below. So we know that A in union with B has these elements: 1, 2, 3, 4, and 6, 7, and 8. So the probability that event A or event B will occur is going to be, we have 7 possible outcomes out of a total of 9. So in this problem, it's going to be 7 over 9, or 0.7 repeating, which is, there's a 77.7% chance that this event will occur. Now, to calculate the union probability, you need to use the addition rule. The probability that event A or event B will occur is equal to the probability that A will occur plus the probability that B will occur minus the probability that A and B will occur. Now, if two events are mutually exclusive, the probability that event A and event B will occur becomes 0. So for mutually exclusive events, this disappears, which means that the probability of A or B occurring is simply the sum of the probability of event A occurring plus the probability of event B occurring. So make sure you understand that. So whenever you see the word or, it's associated with the addition rule. When you see the word and, it's associated with the multiplication rule. Now earlier we mentioned that A and B are mutually exclusive because they don't have any elements shared between them. Now if we were to look at event B and C, these events are not mutually exclusive. The reason for that is because they share 7 and 8, so they're not mutually exclusive. To see this with a Venn diagram, if we were to draw A and if we were to draw B, it would look like this. So A would have the numbers 1, 2, 3, and 4. B would have the numbers 6, 7, and 8. These events are mutually exclusive. As you can see, these two circles, they don't overlap with each other. Now, for B and C, the situation is different. So B has 6 on the outside, and C has 9 on the outside, but on the inside, they share 7 and 8. So B and C are not mutually exclusive because they share element 7 and element 8. So as you could see, because event A and event B are mutually exclusive, the probability that event A and event B will occur is 0 because they never intersect. So that's why this is 0. So that's how you can tell if two events are mutually exclusive. If the probability that they occur together is 0, that means it's mutually exclusive. Now the probability that B and C will occur together, that can happen. We have two elements when they're going to occur together out of a total of 9, so it's 2 out of 9. And let's calculate it using this formula. Let's calculate the probability that B or C will occur together. So that's going to be the probability of B plus the probability of C minus the probability of event B and C occurring together. So B has 3 elements in it out of a total of 9 possible outcomes. So this is going to be 3 over 9. The probability that event C will occur, we have 4 successful outcomes out of 9 possible outcomes, so that's 4 out of 9. And the probability that both B and C occur, they share 2 elements, so it's going to be 2 over 9. But this is minus 2 over 9. So we have 3 plus 4, which is 7, minus 2, that's 5. So now let's calculate this another way. So we can write this expression, probability of B or C occurring, as being the probability of B in union with C. And if we were to figure this out, so B in union with C, we get the sample space, we get the set 6, 7, 8, 9, and I'm forgetting 1, but let's write that first. So it's 1, 6, 7, 8, and 9. And we could see this represents 5 possible outcomes out of a total of 9. So we get the answer 5 over 9. So these are the same. So the reason why this part of the equation is here is because we don't want to count 7 and 8 twice. Because when you calculate the probability of B, that's 3 out of 9. We've included 7 and 8. When you calculate the probability of C, that's 4 out of 9. We've included 7 and 8 twice. So this part of the equation is meant to correct that mistake. So it takes out one set of 7 and 8 because we've included 2 sets of 7 and 8. But if the events are mutually exclusive, then that doesn't matter. This will be 0 if they are mutually exclusive. But now you see how the equation works in giving us these two answers. Now let's talk about joint probability. What is joint probability? What do you think that is? Joint probability is the probability that both events A and B will occur together simultaneously at the same time. And here's how you can calculate it. It's the probability that A and B will occur. And it's also in this way, the intersection, the probability of, it also represents A intersecting B. So remember how A or B corresponded to A in union with B? A and B corresponds to the intersection of A and B. Now, A or B is associated with the addition rule. A and B, that's associated with the multiplication rule. So remember, when we wanted to calculate the probability that event A or B will occur, we had to add PA and PB and subtract it by PA and B, which is the joint probability. When you want to calculate the joint probability, you need to use multiplication. So the probability that event A and B will occur together is equal to the probability that event A will occur given that event B has already occurred times the probability of event B occurring. It's also equal to the probability that event B will occur given that event A has already occurred times the probability that event A will occur. So those are the two ways in which you can calculate the joint probability. Now, for independent events, these are events that do not depend on each other. The probability of A given B is equal to the probability that event A will occur. Now let's make sense of that. If A and B are independent events, and you want to calculate the probability that event A has occurred, no, you want to calculate the probability that event A will occur, given that event B has already occurred, well, that's just going to be equal to the probability that event A will occur, because A does not depend on B. So for independent events, the probability of A given B is equal to the probability of A because A does not depend on B. Likewise, the probability that event B will occur, given that event A has already occurred, is simply equal to the probability that event B will occur, because event B does not depend on event A. So for independent events, in this formula, we can replace this with P of A, and we can replace this with P of B. So the probability that A and B will occur if A and B are independent events, they do not affect each other, is simply equal to the probability of event A occurring times the probability of event B occurring. Or you could write it the other way around. They will be the same. So that's joint probability. Now you might be wondering, how do you know if two events are dependent of each other or independent of each other? And I'm going to have a video entitled Independent Dependent Events in the description section below, which talks about how to calculate the probability of marbles with replacement and without replacement, and that will illustrate this example. So let's say if we want to calculate the probability of, let's say there's some marbles in a bag, color marbles, and we want to calculate the probability of getting a red marble on the first try and then a blue marble on the second try. Now, if this is done with replacement, then the two events are independent events, because the probability of selecting B on the second try, that is getting the blue marble on the second try, will not depend on the probability of getting the red marble on the first try. Because with replacement, after you take out the red marble, you put it back in. So that's not going to affect the probability of getting the blue marble on the second try. Now, let's say if we had the same question, what is the probability of selecting a red marble on the first try and then a blue marble on the second try, but without replacement? Now, this becomes a situation where we have dependent events, because the second event depends on the first event. The probability of selecting a blue marble will depend on event 1, which marble is selected. Because let's say if a blue marble is selected on the first try, then the probability of getting a blue marble on the second try, that's going to go down. And the reason for that is because there's one less marble in the bag. So the probability of getting a second marble is going to be lower than if you would have gotten a red marble in the first try. So that's an example of dependent events. It's when you're removing marbles without replacement. But removing marbles with replacement represent independent events. Also, let's say if you're tossing a coin, if you want to toss two coins and see if you get heads then tails or tails then heads, that will be an example of independent events. The probability of the second toss being heads does not depend on the outcome of the first toss. So that's an example of independent events. Now let's make a distinction between the probability that event A and event B will occur with the probability of AB relative and also the probability of BA. When you see this, this means the probability of A intersecting B. And these events, A and B, they're occurring simultaneously at the same time. Now, sometimes this symbol here, PAB, may represent the probability of A and B occurring at the same time. Other times, though, it could specify an order. What it could mean also is that A is first and then B. So event A occurs first and then event B occurs second. And the probability of BA, that could mean that B occurs first and then A occurs second. So me personally, when I like to write out probability symbols, I like to do it this way. When I write the probability of A and B, I mean that event A and B are occurring simultaneously at the same time. When I write it this way, I'm describing where event A occurs first and then event B occurs second. So here event B occurs first and event A occurs second. Now, these two probabilities, the probability that A and B will occur is equal to the probability that B and A will occur, because these events, they occur at the same time. Now, the probability that of AB doesn't always equal the probability of B and then A occurring. So these two are not always the same. You really have to read the context of the problem. So sometimes they could be used in the same way. Other times they could represent different things. So just be careful with that. So when solving a probability problem, you need to ask yourself, are these two events occurring together, or is one event occurring before the other? Because if you have that situation, then notice that these two, they may not always be the same. Now let's talk about conditional probability. What is conditional probability? In this video, we've talked about it, but I haven't really described it as conditional probability. You've seen it already. So this is the probability of event A occurring given that event B has already occurred. That is conditional probability. It's equal to the probability that event A and a B will occur simultaneously divided by the probability that event B will occur. So the conditional probability is really equal to the joint probability, the probability that A and B will occur, divided by the marginal probability, the probability that the single event B will occur. Now you also have this formula. The probability that event B will occur given that A has already occurred is equal to the probability that A and B will occur, which we can also use the intersection symbol. These two are the same, divided by the marginal probability that event A will occur. So that's how you can calculate conditional probability. It's equal to the joint probability divided by the marginal probability. Now the next formula that you want to be familiar with is associated with Bayes' theorem. And this is related to conditional probability as well. So another way in which you can calculate the probability that event A will occur, given that B has already occurred, it's also equal to the probability that B will occur, given that A has already occurred, times the probability of A divided by the probability of B. So I want to compare the formula for Bayes' theorem with the other conditional probability formula, so you could see how they're related. This should be P of B. So these two are the same, and these two, they look a little different, but in reality, they are equivalent to each other. Because earlier in this video, when we talked about joint probability, the second equation I gave you for the multiplication rule was this. The probability of A and B occurring together is equal to the probability of B given A times P of A. So the difference between the first formula that I gave you for conditional probability and Bayes' theorem is that P of A and B has been replaced with P of B given A times P of A, because they equal to each other based on the multiplication rule of joint probability. So I recommend that you write down these formulas, so whenever you have a problem that you need to solve in your homework, you just gotta pick the right formula and solve it. So now that we've covered Bayes' theorem, let's talk about negation probability. What is negation probability? The probability that the complement of A will occur is 1 minus the probability that event A will occur. So going back to our original problem where we had a sample space of 1 to 9, and event A had the first 4. The probability that event A will occur, we have 4 successful outcomes out of 9 possible outcomes, so it's 4 out of 9. The probability that A will not occur, in other words, the probability of the complement of A, is going to be 1 minus 4 over 9, which is 5 over 9. 1 can be, you can replace 1 with 9 over 9. So 9 over 9 minus 4 over 9 gives you 5 over 9. And you could see how that makes sense. The probability of not getting A. There are 5 elements in S that is not included in A. So the probability of getting any one of these 5 elements is 5 out of a total of 9 possible outcomes. So the probability of not getting A is 5 over 9. So that's negation probability. It's basically equal to the probability of the complementary event, the event that A does not occur. And in some textbooks, you may see this written this way, with a sine wave next to A. So that represents the complement of A, or the negation of A. So that's an example of negation probability. And the reason why this formula works is because the probability of any event occurring is always between 0 and 1. It can't be more than 1. If it's 1, that means that it has a 100% chance of occurring. So let's say that you want to calculate the probability that event B will not occur. You're looking for the complement of B. And let's say you're given the probability of event B occurring, which we'll say it's 0.35 or 35%. You can calculate this by subtracting 0.35 from 1, which will give you 0.65. So according to this, there's a 65% chance that event B will not occur, knowing that there's a 35% chance that event B will occur. So that's an example of negation probability. So that's basically it for this video. I wanted to give you almost all of the formulas that you need to know that's associated with probability that you may encounter in a typical probability statistics course if you're studying this topic. For those of you who want more example problems and how to put these formulas into good use, feel free to check out the links in the description section below. I'm going to be putting a lot of videos on probability and even some on statistics that relate to this material, so that could be helpful to you. So feel free to take a look at that when you get a chance. Thanks for watching.